Okay, so we did equilibrium, and you know what equilibrium is now. And there's three things that affect equilibrium. So it affects when both reactions, the forward and reverse reaction, are equal, and when the reactant and the product concentration are constant. And those three things that affect equilibrium is pressure, and pressure is only relevant to gases. The second thing is concentration, and concentration only applies to solutions, which is actually something that is aqueous. So if you see that AQ, that is for solutions. And the third thing that affects equilibrium is temperature. Right, now we're going to move on to something new, which is called the equilibrium constant, and they show this as K with a subscript C. They call it the Kc or Kc value. So the equilibrium constant is called Kc. Now, Kc is actually an equilibrium constant for a reaction that happens at a specific temperature, and equilibrium is established at that temperature. So it's actually like a value that you have that describes how the equilibrium is going at for a certain reaction at a certain temperature. Now, even though equilibrium is affected by pressure, concentration, and temperature, the Kc value is only affected by temperature. So the only thing that can change Kc is temperature, nothing else. Not pressure, not concentration, only temperature can change the Kc value. Now, what is this Kc value? Right, now there's a few things that you need to know about Kc before we can get into actually calculating it. Now Kc, it's just a value, so it's just a number, and you get that number by using the concentrations of the reactants and products. Now remember, at equilibrium, the concentration of the reactants and products are constant, and we're going to use those concentrations to actually calculate Kc. The next thing you need to know about Kc is that it is a ratio between how much products you have and how much reactants you have. So it's not an actual amount of concentration, it's more of a ratio, and that ratio, because it's just a number, it will have no units. Okay, so all Kc values don't have any units, it's just a number. The next thing about Kc, which I already mentioned, is Kc only changes with temperature. So only temperature has the ability to change Kc. Now, Kc values can be a whole lot of numbers. It can range from very small numbers to very large numbers. Now, those numbers actually tell us something. Now, if you have a Kc value which is greater than 1, so it means it's bigger than 1, it means you have more products present than reactants. So in that specific reaction, the products is more. And if the products is more, it means you have more of the forward reaction happening. Because remember, the forward reaction is where you take reactants and turn it into products. So if you're having more products, it means the forward reaction is happening more. And we say when the forward reaction happens more, we say equilibrium shifts to the right. Now remember, if you write a reaction, all the reactants are on the left hand side and all the products are on the right hand side. So because you have more products, we say equilibrium shifts to the right where the products are, and we say the forward reaction is what is more dominant. Right, now if you have Kc which is less than 1, which means you're going to have a very small number for Kc, then it will be opposite. So if Kc is less than 1, it means that now you have more reactants in the reaction than products. So it means the reactants are more. And if the reactants are more, reactants are normally found on the left hand side. So we say equilibrium shifts to the left. And how do we make reactants? It's by doing the reverse reaction. So you're taking the products and you're turning it back into reaction, back into reactants. So because you're making more reactants, it means you are doing the reverse reaction more, which means you are making more reactants from products. And since reactants are on the left, we say equilibrium shifts to the left. Then if you have a Kc value which is equal to 1, it means the amount or the concentration of the products and the reactants are equal. So both of them are exactly the same. Right, so there is 3 instances. If Kc is greater than 1, it means there's more products. You're doing the forward reaction more. If Kc is less than 1, it means there's more reactants and you're doing more of the reverse reaction. If Kc is equals to 1, it means you're doing both the forward reaction and the reverse reaction equally. So that's why reactants and products are equal to each other. Now you get 2 types of reactions. You get one where you call it homogeneous equilibrium and one where it's called heterogeneous equilibrium. Now you guys have done homogeneous and heterogeneous many times before. Homo means something is the same. So anything where you put the word homo in front of it, it means you're dealing with things that are the same. And hetero means things are different. So every time you put hetero in front of a word, it means you're dealing with two different things. So homogeneous equilibrium is reactions where all of the reactants and the products are in the same phase. Right, they're all in the same phase. Now, what do they mean by the same phase? Now, in a reaction, normally you get in brackets those things where you either see a S or a L or a G or a AQ. That tells you the phase of the products or reactants. So if you see a S, it means the compound is a solid. If you see a L, it's a liquid. If you see a G, it's a gas. If you see AQ, it's aqueous. Right, so if all of them are in the same phase, if they're all either gases, that means it's homogeneous. If it's all liquids, it's also homogeneous. So as long as all of the reactants and products in the reaction are the same, it means it's a homogeneous equilibrium. Then heterogeneous, it's the opposite. It's where the reactants and products are all different. So you might have one reactant that's a gas, one that's a solid, one that's aqueous, one that's a liquid. So all of them will be different. Okay, and we'll see later on how does this homogeneous and heterogeneous equilibrium actually affect the Kc value. Okay, so now that you know that Kc is just a value that is telling you the equilibrium constant for a certain reaction, now we're going to move on to how you actually calculate the Kc value. Now, it's very simple, but you just have to do some practice to get the hang of it. Now, the Kc value is actually just taking the concentration of all of the products in the chemical reaction divided by the concentration of all of the reactants in the chemical equation. Now, do you see that I put products in square brackets and I divided it by reactants, which is also in square brackets. So every time if you see square brackets, this means you are dealing with the concentration of something. So from now on, if you see square brackets in chemistry, it's telling you concentration. So square brackets means concentration, and whatever is in the square brackets, that is what it is the concentration of. So Kc is just the concentration of products divided by concentration of reactants. Now, the reason why I told you what homogeneous and heterogeneous equilibrium is because the Kc is very specific. It doesn't involve every single product and every single reactant. Now, when you are working out Kc values, all of the reactants and products which are solids and liquids. If something is a solid, you'll see a small s next to it. If something is a liquid, you'll see a small l next to it. So anything that is a solid or liquid, those are not included in the Kc value. So if you see a solid or a liquid in a reaction, you are going to totally ignore it. It will not affect Kc. You don't even put it in the calculation. You just ignore it completely. The only things that are included in the Kc values are gases and aqueous solutions. And if something is a gas, you'll see a small g next to it. If something is aqueous, you'll see an AQ next to it. So it is important for you now to look at those things in brackets when you look at chemical reactions. So when you are calculating Kc, you ignore solids and liquids and you only focus on the gases and the aqueous solutions. Right, now when you are doing Kc value, or even when you're working out equilibrium concentrations like how we did in that table, the coefficients which you get from balancing a chemical equation is extremely important. And the reason why coefficients are so important is because the coefficient becomes the exponent when you are actually calculating the Kc value. Right, before we go on to an actual example, when you are calculating Kc values and you are multiplying all of the products to each other, all the products have to be multiplied. So you're not adding anything here, you're not subtracting anything, everything is multiplied. So you're taking all the products concentration and you're multiplying it to each other. And the same thing when you're working out concentration of reactants. If there is more than one reactant, you are multiplying all of the reactants to each other. Right, so let's see a general example of how this works. Right, let's look at this general formula. So you have small a, big A. Now all of the capital letters here are the actual compounds or elements, and all of the small letters in front are the coefficients of it. So just remember, those small letters are coefficients which you get from balancing the equation. Now you have this chemical reaction which is small a times big A plus small b big B, and that is giving you, and again you can see here reversible arrows which telling you equilibrium is reached, and then you have small b big C plus small b d big D. Now if you are going to calculate Kc, remember Kc is equals to the concentration over the products times the concentration over the reactants. And all of the products are multiplied to each other, all of the reactants are multiplied to each other. So let's look at this. If you look here in this reaction, C and D are the products, right? So C and D are products, so that's going to be the numerator, and A and B are the reactants. So the reactants will become the denominator. Now, remember we said the coefficients will become the exponent. So let's see how that actually works. So to calculate the concentration, or to put the concentration, we're going to start with the products and we're going to divide it by the reactants, just like in this formula here. So you're going to take the first product, which is C. So you're going to put capital letter C in square brackets because that tells you its concentration. And since small c is a coefficient of big C, small c will now become the exponent of big C, which means whatever the coefficient is, you are raising that to the power of that coefficient. Then you are going to take the next product, which is big D, and you're going to multiply C and D to each other. So if you don't see anything, it means you're multiplying it, like how you do in maths. Right, so you have the concentration of big D in square brackets, that tells you concentration, and D is the coefficient of big D, so you're going to put this small d as a coefficient of big D. Right, so now you have put all the products. Then you are going to divide it by the reactants, and can you see you also have two reactants? You have A and you have B. So A is the compound, so you're going to put A in square brackets, which telling you concentration of A, and the coefficient small a is what you're going to raise big A to the power of. So it's going to be big A in brackets raised to the power of small a. Then you're going to multiply A to the next reactant, which is B. So you're going to take big B, put it in square brackets, and then raise it to the power of the coefficient, which is small b. So let's go through this one more time. Kc is equal to the concentration of products divided by the concentration of reactants. You multiply all of the products to each other, and you multiply all of the reactants to each other. So you're going to take each product, put it in square brackets like here I did for C and D, and whatever the coefficient is of those products, you're going to raise it to the power or make it the exponent of that specific compound or element. And the same thing for reactants. You're going to have the reactants multiplied to each other, and their coefficients is going to become their exponent. Right, let's do an actual example of this. Right, let's look at this first example. You have N2 plus 3H2 giving you 2NH3, and it's very important for you to know what the states of this reactants and products are, and this you can see by looking at these things in brackets here. Right, now first of all, before you can work out Kc, you need to look at what the states of, or what the phases of the reactants and products are. If it is a solid or a liquid, like we said, you're going to ignore it completely. If it's a gas or aqueous, then you're going to put all of it in the Kc values. Right, so if you look at here, nitrogen is a gas, so that's going to be included. Hydrogen is also a gas, it's going to be included. And ammonia, NH3, is also a gas, so it's all going to be included. And since, can you see that every reactant and product here is a gas, so they are all in the same phase, which is a gas, we call this a homogeneous equilibrium because they're all gases. Right, so if we're looking at this one here, Kc will be equal to the concentration of products over the concentration of reactants. Now in this case, we only have one product, which is NH3. So you're going to take NH3, write it in square brackets, and because the coefficient of NH3 is 2, you're going to square this NH3 concentration. Then you're going to divide it by the reactants, and we have two reactants, so you're going to multiply it by each other. So you have here, the first reactant is N2, so you're going to write N2 in black brackets. Then the coefficient of N2 is 1, so obviously we don't need to write anything for 1. And then you're going to multiply it by H2, which you're going to put in brackets, and then that coefficient of 3 for H2, you're going to make it the exponent of H2. And this is how it is. It's not really that complicated. Right, the second example, here we're dealing with this reaction, which is 4HCl plus O2, giving you 2H2O plus 2Cl2. And if you look here at the phases, can you see this is a gas, this is a gas, this one and this one are all gases. So again, it's all gases, so we call it a homogeneous equilibrium, and all gaseous compounds will be included in the Kc value. So again, we're just going to take the products divided by the reactants. So let's start with the first product, which is H2O. So you're going to put H2O in square brackets. Then you're going to take the coefficient of H2O and you're going to make it the exponent here. So you're making it squared. The same thing with Cl2. You're going to put it in square brackets. The coefficient will become the exponent. So it's Cl2 squared. Then you're going to divide it by reactants. And here you have HCl in square brackets. Now the coefficient of HCl is 4. So you're going to raise H2O, HCl to the power of 4. And then here you have O2 in square brackets. And the coefficient is 1. So it just stays 1. Right, now let's do one where you don't have a homogeneous equilibrium, where the reactants and compounds are actually in different phases. So let's look at this example. So you have here calcium carbonate, which is a solid, giving you calcium oxide, which is also a solid, plus CO2, which is a gas. Now remember, we said solids and liquids, you are going to ignore it. The only thing you're focusing on is gases and aqueous. So before you even start writing the Kc value, we're going to scratch out everything that's solid and liquid. So can you see calcium carbonate is a solid? We're going to ignore that completely. Again, can you see calcium oxide is a solid? We're going to ignore it completely. So the only thing we're left with is CO2. Now CO2 is a product, so we're going to have to say products over reactants. So you're going to put CO2 in square brackets and the coefficient is 1, so you're just raising it to the power of 1. Now in this case, can you see that the only reactant we have was calcium carbonate, but because it's a solid, we have to ignore it. So we can actually put this as CO2 over 1, or you can just ignore this completely. So the Kc value of this whole reaction is just concentration of CO2, and that's it. So we're ignoring this completely, so you act like it's not even there. Right, the next example is this one here, where you have H2SO4. This one is aqueous, so remember aqueous, we have to include it, plus 2H2O, which is a liquid. Now remember, we said liquids we ignore, so I'm going to just go and scratch this out already, because we're going to ignore all liquids. And this will give you SO4 2 minus, which is aqueous, so aqueous we're going to include, plus 2H3O plus aqueous, so we're going to include it. So we're going to include all of them besides the H2O liquid. Right, so again, we're going to say concentration of products divided by concentration of reactants. Okay. So now we have here SO4 2 minus, so we're going to put SO4 2 minus in square brackets. This 2 minus, you're going to include it in the square brackets. Right, and then the coefficient here is a 1, so you're just going to make this a 1, you're going to leave it as 1. And then you have H3O plus here, and you're going to write that in brackets. And then can you see it has a coefficient of 2, so it means we have to square this H3O plus. Then we're going to divide it by the concentration of reactants, which in this case we're only including this reactant, so it's H2SO4 in square brackets, and the coefficient is 1, so you just leave it as 1. And this is how you're going to write Kc for this specific reaction. Now we're going to move on to some of the examples in the textbook, and this is where we're actually going to use values of concentration with actual numbers. So far we have just been writing Kc values without actually doing a calculation. And when you write Kc without the calculations, we call it the Kc expression. So you're just writing how you will actually calculate it, but you're not actually calculating it. So let's go into the actual calculation. Right, we're on example 5 on page 87 of your textbook. It says here hydrogen and iodine are mixed in a closed container and heated up to 400 degrees Celsius. At equilibrium for the reaction H2 plus I2 giving you 2HI, it is found that the concentration of H2 is equal to the concentration of I2, which is 0.5 mole per decimeter minus 3, and concentration of HI is 3.5 moles per decimeter minus 3. Calculate the equilibrium constant at 400 degrees Celsius. Right, now first of all, before you can calculate it, you need to write the Kc expression, which is how you're going to calculate it. So can you see here, each of these reactants and products are all gases. So since they're all gases, we're going to include them all in the Kc value because gases are always included. So it's going to be the concentration of the products divided by the concentration of the reactant. So this is the product HI. So you're going to say HI in square brackets. Then HI has a coefficient of 2, so you're going to square it here. Then you're going to divide it by the concentration of reactants. So here you have H2, you're going to put it in square brackets. There is no coefficient, so we will just ignore that. And you're going to multiply it by I2 in square brackets, which also has a coefficient of 1, so you just leave it as 1. Right, so now that you have the Kc expression, we can actually substitute the actual numbers or values of concentration to get the value of Kc. Now they told us that HI's concentration is 3.5. So we are just going to now substitute like a normal equation. So we have here HI squared. So we're going to take whatever the concentration of HI is, which is 3.5, and we're going to square it. So you basically now are just putting values in where you see the actual reactants or products. Then you're going to divide it by H2's concentration, and here they told us H2 is 0.5, so you're going to put 0.5 here, and then this is multiplied by I2's concentration, which they said is also 0.5, so you're going to multiply it by 0.5. Then you're going to calculate it normally with a calculator, and you will get an answer of 49. Now Kc values does not have units. There is no units because, like we said, it's just a ratio telling you how much products there is to reactants. There is no units. So Kc value for this is 49, and you just leave it as a number. Now we said if Kc value is greater than 1, remember we said here before, if Kc is greater than 1, it means you have more products than reactants, and the equilibrium shifts to the right and you have more of the forward reaction. So since here Kc value is 49, which is way higher than 1, it means you are making more product. So in this case, the product is Hi. So you're making more Hi compared to how much reactants you have, which means the forward reaction is happening more and equilibrium is shifting to the right where Hi is. Right, let's do another example. Right, so you have here example 6. Carbon reacts with carbon dioxide to form carbon monoxide in a closed container at a certain temperature according to the following equation. So you have carbon plus CO2 giving you carbon monoxide. Now, if we look at carbon, can you see carbon has a S? And S means carbon is a solid. So we said solids, we are totally ignoring it. They are not involved. You just ignore it completely. So I'm just going to go here and scratch out carbon already so I know I don't have to include it. Then we have your CO2 gas, so we're going to include that, and we have carbon monoxide, which is a gas, and we're also going to include that. Right, so it says if the concentrations of the carbon dioxide and carbon monoxide is respectively 10 moles per decimeter cubed and 4 moles decimeter minus 3 at equilibrium, calculate the equilibrium constant. So before we calculate it, we need to write the equilibrium expression. So to do that, you're going to say concentration of products divided by concentration of reactants. Here the product is CO, so you're going to put CO in square brackets, and the coefficient is 2, so you're going to raise it to the power of 2. Then you're going to divide by the concentration of products, of reactants, and since we are ignoring carbon because it's a solid, we're only going to include CO2. So you're going to put CO2 in square brackets. The coefficient is 1, so you just have to leave it as a 1. Right, now that we have the expression, we can just substitute and then just calculate the Kc value. Right, so they're telling us carbon dioxide is 10 and carbon monoxide is 4. So where you see carbon monoxide, you're going to put a 4 and then square it. And then you're going to divide it by carbon dioxide, which is 10. And that will give you a Kc value of 1.6. Now 1.6, it's not very high like how we did in this example of 49. But it's greater than 1, which means because it's greater than 1, you have more product than reactant, so you have more of carbon monoxide compared to carbon dioxide. So it means the forward reaction is happening more. That's why you're making more of the carbon monoxide product, and equilibrium rise to the right hand side where carbon monoxide is.